Okay, thank you. So it's my turn to talk about Hyper-Kamiokande. So there is a Kamiokande family of experiments that started with Kamiokande itself in the Kamioka mine in the 80s. So this was 3,000 tons, of pure water in a cylinder underground in Japan, in the Kamioka mine. And then there was a progression, and it was scaled up in 1996 to SuperKamiokande, which is the same concept but with larger mass, 50,000 tons now. And that's a picture of the inside of Super K. So the detection mechanism is that you have a neutrino that comes into the detector and strikes a molecule of water and produces a charged lepton and some other charged particle possibly. And then if the charged particle is moving faster than the light in the water, then by the Cherenkov effect, it shines a cone of light which intercepts the wall of the detector, drawing a ring or a circle. And so these detectors have particle ID capabilities because, as was told earlier today, if the particle is the muon, because the muon is heavy, it moves forward steadily and it draws a sharp ring before going under threshold. While if it's an electron, because it's lighter, it's the same mass as the electrons of the medium, so it scatters more and the ring is more diffused. And even if you have a pi zero, and if the two photons from the decay have a large enough angular separation, then you can see two rings and separate. So there is particle ID, and then you can reconstruct where the vertex of the interaction is because, for example, because you know the opening angle of the Cherenkov cone in the water, and so from the ring you can find the apex of the cone. That's the point where the interaction happened. And then you draw the line that goes through the vertex and the middle of the ring, and that's the direction of motion of the charged particle, which is correlated to the direction of motion of the incoming neutrino, more so the higher the energy of the neutrino. But even in this famous plot, you can see from Super K that even for solar neutrinos that have low energy, meaning few MeVs, so for example, you have a flat background on top of which there is a signal from solar neutrinos that is highly correlated to the angular position of the sun at that moment. So we can find the particle ID and the vertex and the direction, and then just measure the energy by the amount of light. And so the next step in this kind of progression is Hyper-Kamiokande, that is now 260 kiloton as opposed to 50 kiloton. So in this table, I summarized the main changes. So the fiducial mass is increased significantly. Now the photocathode coverage, this is the the fraction of the area of the wall that is covered by photocathodes. So it's the fraction of photons that you can hope to detect, is the same in Super K and Hyper K. But because Hyper K is bigger, then that means that 11,000 PMTs have to become 40,000 PMTs. And these PMTs are more sensitive than the ones in Super K, but I will explain later in more detail exactly how. And then there is an optical separation, so there is an ID and an inner detector with the PMTs looking inwards, and then there is an optical separation, and then outer PMTs looking outwards at 1 or 2 more meters of water layer used for VITO, and there are 15,000 more PMTs there. So this project has been approved and funded 1 month ago in Japan, and the construction will start in April. So now I go through the different elements of the detector. And of course, it starts, we have a beam, same as T2K, which I should have mentioned in the family of experiments linked to Kamioka. So there is a beamline at J-PARC that was already described today, in which, the usual way, you slam protons onto a target and get things among which pions, and then with a magnetic field select pi plus or pi minuses, and then guide them into this decay volume where they decay and make your beam of muon neutrinos or muon antineutrinos, and then you stop them before the muons decay. So the detector is off axis, which is a trick that now most experiments use, because due to the two-body decay of the kinematics of the pion decay, going off axis allows to narrow the range of energies. So the J-PARC beam is centered around 600 MeVs, and the value, of course, is chosen so that when you, together with the distance between the near and far detector, you set the maximum of the oscillation at the far detector. So the beam will be largely upgraded to more than twice its power before Hyper-K starts taking data, which is in 2027, as well as the repetition cycle will be more than halved, and this leads to larger statistics. So then, after the beamline, there is the Near Detector, which by now I would say is an entirely standard feature of the long baseline experiments. It's an essential part, as was also told today, to really reduce quite dramatically the systematic errors. So it's used to constrain the parameters when you make the fit for the far detector data, and essentially to measure the profile and the composition and the spectrum of the beam before oscillations have happened, and to measure the interaction rates before the oscillations have happened. So in T2K, the systematic error associated to interaction rates is around 6%, and we need to reduce it to 3% in Hyper-K in order to measure delta CP as good as we want. So several things are on the way in order to achieve this goal, and one of them is the upgrade of the Near Detector. So the Near Detector includes an on-axis detector that is this INGRID. It's a cross of alternating iron and scintillator plates. It's on-axis, so the beam goes through the center of the cross, and it's essentially used to measure with high precision the direction and just the stability of the beam. And then there is a suite of off-axis detectors that are sitting 2.5 degrees off the main beam, so the same off-axis angle as the far detector. And they're magnetized. And so there are many pieces in there. There's an electron calorimeter, a pi0 detector, some TPCs, and these scintillating fine-grained detectors. And new detectors will be built very soon and largely before Hyper-K starts taking data, including time-of-flight detectors and some horizontal TPCs that have a wider angle acceptance, and a so-called super fine-grained detector that has a very fine granularity. So these are all contributing to suppressing the systematic errors. And then there is a new idea. This one is new. So we have a near detector, say 300 meters downstream, and then a far detector 300 kilometers downstream. But now we add one more detector in between. It's called Intermediate Water Cerenkov detector. And also it's a Water Cerenkov, so it's the same technology and measurement mechanism as the far detector, so that when you take the ratios, systematics largely cancel. So this is a 1 kiloton scale kind of detector located 1 or 2 kilometers downstream. This is essentially as big as the original, is of the same order as the original Kamikande, right? Which is quite amazing. And it's mounted on an elevator, which can run for 50 to 100 meters underground. So the idea is that moving this detector, you can sample different off-axis angles and that's equivalent to measuring at different beams centered at different energies. And so the strategy is that by taking linear combinations of the different measurements taken at different points, you can probe and sample very precisely the full profile of the beam. So this is used again to control the systematics and to measure the backgrounds. And incidentally, you shouldn't be thinking that this moves continuously. I think the idea is that you put it at 2.5 degrees and measure for 1 year or so, and then move it somewhere else and measure for 1 year, and then repeat. So this is quite smaller than Hyper-K, of course. So in Hyper-K, we want to have an error in the vertex reconstruction of around 30 centimeters order of magnitude, depends on what the energy is. But because this detector is much smaller, we have to have a 2 centimeter level of the vertex reconstruction. And for these, we are going to instrument this detector not with the standard large PMTs, but with multi-PMTs that I will describe in a little bit in more detail. But essentially, they are assembles of many small tubes, so they have larger segmentation, and they're just more precise in making the position measurements, right? So that's the other main ingredient for killing the systematics, is this new detector. And in 2021, so next year, we will run a test of a prototype for this intermediate water Cerenkov detector at CERN in a beam. So this will be even smaller. It will be order of 100 tons. And we target it with a beam of charged particles, so protons, electrons, pions, muons, as well as neutrons. And of course, the idea is to test the detector and to understand the detector response, and particularly the pion scattering and the production of secondary neutrons. Right, so then finally there is the Far Detector. So this is the map of Japan, and over here is where the beam starts, and then a J-PARC, and then it goes 295 kilometers. And then when it gets here on the right, 2.5 degrees, is the Kamioka mine where Kamikande was and where SuperKamiokande is and will continue to be, right? While on the left, so under a different mountain, but at the same off-axis angle, will Hyper-K take place under this mountain. And so the place has been selected, and the geological survey is ongoing. So what do we put on the walls of Hyper-K? This is the only part of the detector that is actually sensitive and capable of measuring anything. So we need something to detect light, and I listed there some fairly obvious requirements for these photosensors. First of all, because the physics program of Hyper-K is extremely rich, and so it spans from solar neutrinos that have MeV energy scale to higher than GeV for atmospheric neutrinos, for example. So we need a wide dynamic range, and then naturally we want good charge resolution and good detecting efficiency and good timing resolution and low background in all the glass, mostly in the glass of the PMTs and really in every piece. And the interesting point is that because Hyper-K will be almost 80 meters tall, which is quite scary, so it's twice as much as SuperK, there will be a tremendous pressure at the bottom. And in SuperK, the tube's already exploded. So for Hyper-K, we need to make sure that they're pressure resistant. So the baseline choice is very conservative. The whole spirit of the experiment is very conservative, really, is to use this large half-meter diameter Hamamatsu box and line dynode structure PMTs, similar to the ones used in SuperK, but newer and more efficient. So these are 3 plots to explain the better performance of these photosensors. First of all, they have a larger detection efficiency which is like the product of the collection efficiency and the quantum efficiency. Twice as good for single PE, for single photoelectron signal. And then the timing resolution also is twice as good, from 2 nanosecond to 1 nanosecond, and then the charge resolution also is almost twice as good, which is all excellent, although it does bring in the problem that being these photosensors more sensitive to the signal, they're also more sensitive to all the backgrounds. And so we have to control well, we can't really control the thermal emission, but we have to control the radioactivity part of the dark noise even more to this level. This is the dark rate per PMT. And 140 of these new Hamamatsu PMTs are already installed and, in fact, taking data in SuperK right now. But that's not the only choice. That's the baseline choice. We have an alternative, which has these multi-PMT that I mentioned before. You see a picture here from the concept developed by the K-Magnetic collaboration. So it's a vessel of a half-meter diameter containing 19 small, cheap 3-inch PMTs. And the idea is to read out each of the tubes, of the small tubes independently, thus multiplying largely the number of electronics channel and the problems for the data acquisition system. That's one of the things I work on. So you can look for local coincidences between these tubes, and also there is directional sensitivity depending on which ones fire, which was entirely absent in the big, let's say, monolithic big PMT, and they're less sensitive to magnetic fields. So each of those points is now a collection of 19 different cells. So these multi-PMTs help in, because they have a better timing resolution, because the transit time, that's the time for the photoelectron to go from the cathode through the dynode structure. Because they're smaller, the transit time is smaller, so the spread in the transit time is also smaller, and that is the origin of your uncertainty in the timing measurement. So the timing resolution is twice as good as for the Boxen line. And in this plot, you see how that helps. So the vertical axis is the error in the vertex position, and the horizontal axis is the distance from the wall. So essentially, adding these multi-PMTs allows to reduce, in particularly near the wall, the error on the vertex reconstruction. And this is for the low energy 10 MeV case, where we are around maybe 40 centimeters. And this is for the 500 MeV case, close to the beam energy, where we are more around 20 centimeters. And that's very important, because even gaining a few centimeters is important. So if you know better where the vertex is, you're more confident when you're cutting on the fiducial volume, so you can cut closer to the wall. And because of the circular geometry, most of the water is in fact near the wall, so you gain a lot of fiducial mass. And these are the choice adopted, as I said before, for the Intermediate Water Cerenkov detector, and we're looking at it for the Far Detector as well. And still there are other alternatives, like these Chinese multi-channel plate PMTs that are used in Juno, and these hybrid PMTs that have a avalanche diode at the back for the multiplication stage. And so we haven't decided yet, but it's likely that Hyper-K will adopt a hybrid system in which the wall, the ID wall, is a combination of different photosensors. So let's say half of them are 20-inch Boxen line, and the other half is some combination of multi-PMTs or something else, while the OD is a combination, as yet undefined, of 3-inch and 8-inch embedded in a wavelength shifting plate that trap the light through total internal reflection and thus increase the light acceptance. But we cannot use this trick on the ID because it spoils the time resolution, because you have to wait for the photons to propagate through the plate. So that was the description of the detector, and now what does it do? It does lots of things. So let's start with the atmospheric neutrinos, which of course have been measured already by Kamikande and SuperKamiokande, so we can do precision measurement of the mixing parameters. And then there is this one nice measurement, which is that the new mu flux suffers a matter effect when going through the core of the Earth and turns into nu-e before going to Hyper-K on the other side. But this enhancement depends on three things. So it depends on the hierarchy, and it depends on the octant of theta 2,3, and it also depends on delta CP. So that is our handle for measuring both the mass ordering at the 3 sigma level after 10 years of running, and the octant at the 3 sigma level after 10 years of running, which is like the minimum amount that we conceive to be running for. So then we have the beam neutrinos. These come at high energy at known time, and so we know when they're coming through GPS synchronization, and the triggering is very easy. And these we can use to look for new E appearance in the new ME beam. So here you see two plots for the number of events that you expect to collect in the neutrino mode and the antineutrino mode. Statistics is the same because the beam time in the antineutrino mode is 3 times as long as for the neutrino mode to compensate for the fact that the cross-section is a third. And so the 3 curves are, or 4 curves are for different values of delta CP. And that's the way we can measure delta CP that, as we know, is already disfavored. The conservation is already disfavored around the 3 sigma level now, according to the most recent paper by T2K that has been accepted by Nature this month. So, but around this point, which is the favored point, we can measure delta CP for with 8 sigma. We can reject the delta CP conservation at 8 sigma after 10 years. And also these curves show the error in the angle in the measurement of delta CP, which spans between 7 and 22 degrees, depending on what the true value is. And then we have the solar neutrinos that also have been measured by SuperK, and so we can do precision measurement with Hyper-K. Okay, I don't want to go into this tension with Kamland, but there is, again, an effect of, so some of the new E oscillate into new mu or new tau on the way to the Earth, but then they are regenerated into new E when going through the Earth. So there is an asymmetry between day and night, and we can measure that asymmetry, you see, after 10 years with 8 sigma. That's constraining the matter effect. And then I think more interesting is this measurement of the upturn probability. So this is the probability of survival, probability that a neutrino emitted with an electron flavor in the sun still has the electron flavor when measured on the Earth. And so this, of course, has an oscillatory shape, and it rises in the 2 to 5 MeV region, but the way it rises is model dependent. So it's different for a standard model as when sterile neutrinos are there. So measuring this curve allows to measure the existence of sterile neutrinos. And so if we have a 4.5 MeV threshold, which is what SuperK had, we can measure that after 10 years at 3 sigma. But in fact, if we can lower the triggered threshold to 3.5 MeV, which we think we can do, that's one of the things I work on, this becomes 5 sigma. Then the supernova. So we cannot see the new E's in the initial burst phase very well because they need to interact on the neutron, and there is no neutron available in the water because the hydrogen only has the proton and the neutrons in the oxygen are bound by nuclear forces. So we can only see the anti-new E, but those we see very well. So Dune is better suited for looking at the new E signal, but Hyper-K has a significantly larger fiducial mass, so we just have more statistics for the overall signal. And so the 1987 supernova, for example, the only one we saw, which was measured mostly by SuperK with around 10 or 20 events, depending on how you want to count, would give 3,000. Supernova in the galactic center would allow 10 to the 5 events precision measurement of the supernova explosion, and we could even see supernova in a different galaxy at the same level as the 1987 one. And that's one of the things I work on is, so we don't know clearly when the supernova is coming, and also it produces many events, but they are spread over like a 1 minute, very long time scale. So we need to be continuously buffering at least 1 minute of data and running a fast enough trigger algorithm to analyze in real time and look for a supernova signal. And if it finds it, save the data to some disk that is large enough to contain 1 minute of raw data. Analyze it very fast, find the direction of the supernova within 1 degree, and then tell everybody else on the planet to point the telescopes there, right? And then there are also the relic neutrinos. So that's not neutrinos from a single burst, but rather the neutrinos emitted by all the supernovae in all the history of the universe. They've never been measured, and we can measure them by adding gadolinium because there is a neutron produced and a positron in the reaction, so we can tag the neutron with gadolinium. And notice that gadolinium, 5 tons of gadolinium are being added next week, I think, in SuperK, right? And that's, we have the convenience of having SuperK as a kind of a prototype for Hyper-K. So if that goes well, then we do it for Hyper-K. And so we can measure the relic neutrinos in this window. And there are some other fancy ideas to actually measure the dark matter, because dark matter annihilates in the sun and shoots neutrinos to Japan, and we see those. And finally, the proton decay. I listed here, where somebody did many modes of decay of the proton. And in most of them, Hyper-K can make a significant measurement and in fact reach the largest of all sensitivities at the 10 to the 35 years level, because in fact Water Cerenkov detectors were initially conceived for measuring the nucleon decay, not really for neutrino physics, and they're very well suited for this. So the golden mode for Hyper-K is proton goes into positron pi 0, because we can see all the products. And through neutron tagging, it's essentially, especially if the free proton is the one that decays, it's a background-free search with a 3 sigma discovery for potential. And then this other main mode, that's the golden mode for Dune, because Dune can see the kaon, but in the case of Hyper-K, the kaon is below the Cherenkov threshold, so we cannot quite see it, but we have to wait for the kaon to decay, and then we either see the muon or the pions. And because there is this chain of the neutron capture and decay, there is a definite time structure to the signal. So we can find it that way and also have a 3 sigma discovery potential. And then I conclude with the timeline of the detector. So we're here now. The geo-survey is ongoing. So next year, we have to start producing all the 40,000 or so PMTs. And then the cavern excavation begins until in 2026 installation is concluded, water filling, and then we start taking the data. And so to summarize, I would say that Hyper-K is good and it's happening.